Hi, it's Mr. Blystone here, and here's the second video in Unit 1 for Calculus. We're talking about rate of change by equation, graph, or table. So let's get started. So, again, this is just kind of a review. You've probably seen this before. A function. We have the symbol f of x. Pronounce it f of x. You've seen that, I'm sure. Or f at x. That's not the way I've seen it pronounced, but it could be where you are. Of course, you know how to evaluate it. f of x is 3x plus 7, plug in 5, like that. So we have a particular equation, which is f of x equals 3x plus 7 for a linear function, and the general is y equals mx plus b, where m and b are constants. And if you should remember, m is the slope, b is the intercept. Let's look at some general functions. So we have linear lines, form of y equals mx plus b. Quadratic parabolas, ax squared plus bx plus c. A, b, and c are constants. The leading coefficient can't be 0. Polynomial has this form. It can have as many degrees as it needs to have. And its leading coefficient, again, can't be 0. All parabolas, quadratics, or polynomials. A power function is basically a polynomial, but just the first one term, just like one term, ax to the n. Exponential function a times b to the x, where a and b are constants, where a can't be 0, b can't be 1, and it has to be greater than 0. So, a rational function is the division of two polynomials. Absolute value has something times something in the absolute value symbol. And trigonometric, circular, or they also call it periodic, sine, cosine, tangent, cotangent, cosecant, secant, and secant, etc. All those. Also not here are logarithmic functions. Don't forget those. The inverse of exponential functions. And then also the inverse trig, arcsine, arctangent, etc. Those aren't there, but they should be there. All right, let's look at an example. So now we have a graph. Only a graph, no numbers. So it says figure 1-2a shows the graph of a function. At x equals a, x equals b, and x equals c, state whether y is increasing, decreasing, or neither as x increases. Then state whether the rate of change is fast or slow. All right, so if we look, one good way is to take our point and kind of draw a line through it. And if we were to do that, similar to what I did there, kind of similar, like that, if it were like that. A little more tangent, but you get the point, I think. See if I can rotate that. I can. If I did that, all right, it's increasing. So we can definitely say that at x equals a, it's increasing. All right. X equals b is the third point here. We can see that it's going down if we kind of draw our line. And we do a better job than that, hitting the point, like something close to that. We can see it's going down. So it's definitely decreasing. Right. X equals c. We're at the top of the graph here. And it's right there. If I draw a line, it's flat. It's a flat line there. So that means at x equals c, it's not increasing and it's not decreasing. So it's neither. All right. Now let's talk about fast or slow. Well, if we had to say comparatively, I would say that this is pretty steep at x equals a right here. This is pretty steep. So I would call that fast, or faster, anyway. This here at x equals b is less steep. Not quite as steep. So I could say that's slow. And well, here it's neither increasing nor decreasing. So its rate of change is 0. It's not changing. So that's how we can use a graph with no numbers to talk about rate of change. All right, now let's look at a graph with numbers. All right, figure 1-2b shows the graph of a function that could represent the height, h of t, of a soccer ball above the ground as a function of the time t in seconds since it was kicked into the air. A says estimate the instantaneous rate of change of h of t at time t equals 5. And B says give the mathematical name of this instantaneous rate and state why the rate is negative. Okay, so let's just analyze the graph here. It's going up at, 2 seconds. It's already close to 60 feet in the air. At 4 seconds, a little between 3 and 4, it's at its top, which is clearly about 70 feet. Here at 5 seconds, it's 60 feet in the air and it's going down. So we can see, we want to estimate this instantaneous rate of change. Well, remember I told you the idea of a line. The instantaneous rate of change can be represented by what we call a tangent line. A line that goes through at one point. So if I draw a tangent line, excuse me, not that line. I don't like that line. I like a line that's just, okay, something. Let's see here. Let's go a little more tangent. Let's do that, and I can move it. That's the beauty of the software. I can move lines where I want. Yeah, that's better. If I do that and I extend this line, so we can kind of see. Okay, so let's see if we can name 2 points on this line. Because we can name 2 points, we can name a line. Well, here I see a point at 6, 60. So here I see a point at 6, 60. I'm sorry, 5, 60. That was my mistake. In fact, that's what we want. We want 5. Good. 5, 60. And then I can see that it should be about 8, 20. 8, 20. I could say that those are 2 reasonable points. So, if we remember, to find slope, it's y2 minus y1. So, 20 minus 60 over x2 minus y1, or x1 rather. So, over 8 minus 5. 20 minus 60 is 40. Sorry, negative 40. 8 minus 5 is 3. So it's about negative 40 over 3. So that is our slope of this line, negative 40 over 3. So that would be about the instantaneous rate of change at that time. About negative 40 over 3. You could use your calculator, now that number doesn't necessarily tell us much. We don't know too much, So if you use a calculator, it's about negative 13.3, repeating. So, part B, if you watched our last video for section 1, you will remember that this mathematical name is called the derivative. And why is it negative? Well, because h of t is decreasing. All right, let's look at now an example with a function with values, not with an equation. So it says, figure 1-2D shows a graph of t of x equals 40 times 0.6 to the x. The probability that it rains a number of inches x in a particular place during a particular thunderstorm. Probability that it rains 1 inch, t of 1, is 24%. By how much and in which direction does the probability change from x equals 1 to x equals 1.1? What's the average rate of change from 1 to 1.1 inches? Make sure to include units in your answer. Why is the rate negative? B says write an equation for r of x, the average rate of change from 1 to x. Make a table of values for r of x for each 0.01 unit from 0.97 to 1.03, and explain why r of x is undefined at x equals 1. C says the instantaneous rate at x equals 1 is the limit that the average rate approaches as x approaches 1. Estimate the instantaneous rate using information from part B. Name the concept of calculus that's given to this instantaneous rate. Okay, we've got a lot to do on this example. So let's just start in. Let's start with part A. So it wants the change from x equals 1 to x equals 1.1. Okay, so what we want is, so how much and in which direction. So we just need to know the two values, p of 1 and p of 1.1. So for A, p of 1. Well, I'm going to take my calculator and I'm going to plug this into a calculator. So if I have a calculator, I can plug this in. Now, the way I suggest you do this is you go to where you plug it in a TI calculator, to the y equals, and just plug in your function. So I'm going to do that. 40, parentheses, 0.6 to the x, and close the parentheses. Then the first thing I'm going to go to the second window, which gives me the table set up. And I'm going to make sure to put the independent, INDPNT, set it over to ask. And then I'll go to second graph, which is a table. So now I have a table. So I can just plug in the values I need. 1 and 1. Wait, 1. Well, I know P of 1 is 24. It says that in the question. And I know that P of 1.1, according to my table here, 1, is equal to 22.805. So let's see here. Well, it clearly is going down. It's getting less. So, by how much? Well, by 2.805%. So it goes down by 2.8, well, not 2.805, sorry. Let's do the subtraction. I'm not right. So 24 minus 2.805. 24 minus 22.805, I should say. I'll get this right. 1.195 by 1.195%. Okay. So what is the average rate of change? So the average rate of change is just the change in P over the change in X. So the change in P, we can just say it like this. P of 1.1 minus P of 1 over 1.1 minus 1. So we would get that this is equal to negative 1.195 over 0.1. Now, if we just divide by 0.1, all we have to do is move the decimal point, and we get negative 11.95, and that would be percent per, and let's check our time frame. Percent per inch. Yeah. Percent per inch. So, that's our answer to that. Okay. So, C, the instantaneous rate. Oh, B, sorry. Okay, so for B, I think we should do this using a little technology. So, I'll be right back, and we'll see you in Desmos. Okay, so here in Desmos, let's go ahead and graph our first function. We know that P of X equals 400 times 0.6 to the X. Okay, it's a little off. Let's squish this down a little bit. Like that. That's our function. Let's move this out because we're going to need to see some different values, some lower values. Good. Now let's squish it like that. That's a little bit better. Okay. So there is P of X. Now, part B asks us to write an equation for R of X. The average rate of change from X to 1, or 1 to X, it doesn't matter. Let's just do it X to 1, okay? So remember how we did it for the last one. We took P of 1.1 minus P of 1 over 1.1 minus 1. So instead of 1.1, we're doing X, so we'll call that P. Let's put this in parentheses so we can do this. P of X minus, and we're doing it at 1, so P of 1. We're going to divide that all by X minus 1. So that is our average rate of change. So that is an equation for our average rate of change between 1 and some other number on this graph that's X. So this blue graph represents the average rate of change between 1 and some other number here, X. So, now let's see what we do. So we're making a table of values. So let's do that. So we go here and we just take this and we can make a table of values. Okay, so it wants the table of values from 0. So let's put 0.97, 0.98, 0.991, 1.01, 1.02, than 1.03. So if we take a look at this table of values, well, we see it's negative 123.5, negative 123.2, negative 122.9, undefined there, negative 122.8, negative 121.9, negative 121.6. So if we're going from getting higher, we're decreasing, or rather we're increasing up to some number. And here we're increasing past it. But if we go backwards, we're decreasing closer to some number between negative 122.9 and negative 122.8. Some number in there. It's clearly our limiting number. How can we be sure? Well, let's move this out a little bit. A lot bit, actually. If we do it that way, now let's move the graph over. Take a look at our dots here. These are the dots on the table, these blue dots. Notice how they're evenly spaced. So clearly, and there's no dot at x equals 1. It's undefined. So something goes there. We can tell that those dots are going towards some point in the middle there, in between there. So it's going to be somewhere in between there. Now, why is x undefined at that point? Well, let's think about that. So why is r of x undefined? Well, let's see here. P of x is our function. P of 1 is that. At x equals 1, P of 1 is 24. P of 1 is 24. 24 minus 24 is nothing. 1 minus 1 is nothing. 0 over 0. If you watched the last video, we call that an indeterminate form. We can't tell anything from it. We don't know. So because we don't know, we have to do further work. So we just say it's undefined. Because we just don't know. 0 over 0 tells us nothing. So it's undefined. Now for part C, we want to find a value in between. We want to find that value. So what can we do? Well, if we're looking at these again, we notice that they're evenly spaced. And so that clearly P of R of 1 should be the value we expect is somewhere in the middle here. In the middle tells me an average. How can we take an average? Well, we can say an average is P of 0.99 plus P of 1.01 all divided by 2. I'm sorry, not P. That would be the average of P. We want R. Excuse me. I used the wrong one. That's why I do these live, so you can see mistakes. R of 0.99 plus R of 1.01 divided by 2. And we get negative 122.598. Now, let's just call this a point. So we'll call that our y point, and we'll call this 1, comma. And let's make the point, it was in black, let's make it a little bit easier to see. Let's put it in orange there. Yeah. So look, clearly that point is right. Is exactly what we expect. Is it defined? No. 0 over 0 says it's not defined. But clearly, that orange point goes right in line. It fits in that line beautifully, right in a row. On that graph. It's on the graph too. So it's everything we expect. So that would be our instantaneous rate at that point, negative 122.598. Okay, another example. Example 4, and here's one with just a table. It says a mass is bouncing up and down on a spring hanging from the ceiling, like figure 1-2e. Its distance y in feet from the ceiling is measured by a calculator distance probe, each 1/10 of a second, giving this table of values in which t is time in seconds. We want to know how fast y is changing at each time. T is 0.3, t is 0.6, and t is 1.0. And then b at t is 0.3 is the mass going up or down, and we want to justify our answer. Okay. So we have a table of values, and let's just analyze what's going on. So this is the ceiling, here's our mass, and it's got a spring. And this is the distance from the ceiling. So it's going up, so the block's going down, the block's going down, the block's going down here. Then between here it starts going up again, and up again, and up again, and up again, and up. And it reaches 2 inches to the ceiling, and then it goes back down again, and back down again. Like a spring should. So I think that with a table of values like this, now, if you're just given a table of values and you really don't have anything, you could use a calculator that uses tables. I think since I've got a computer in front of me, let's use a spreadsheet. So I'll be right back and put these values in a spreadsheet, and let's see what we can do. Okay, so we can now see the chart of values. I put some space in here because here's what we're going to do. We're going to find first the change in y of t. Then we're going to find the rate getting close to the values we want. We want 3, 6, and 1.0. Or 0.3, 0.6, and 1.0. So, we're going to find the values going between 0.2 and 0.3, and then 0.3 and 0.4, and then we'll find an average of those, and that'll be about right for our instantaneous rate. So, our change is equal to the amount in this cell B4, which is the value of 0.3, minus y of 0.3, minus the value in B2, which is the value of y of 0.2. So that's our chain. So we can fill this out. Let's see if this will work. I think it will. So I'm just going to delete these other values we don't want. Hey, one more. All right, so these are our change values. So now we'll find the rate. To find the rate, here, all we have to do is divide that value by 0.1. So we'll divide it equals that value divided by 0.1. And that's our rate. So that's our rate. So I can erase all the intermediate values. Here, okay. So to find our average rate, we do something simple that we did before, similar to that. We take the two values. So in this case, this value plus this value, and we divide by 2. And that creates our our instantaneous rate of change at the points we're looking for. So we want these 3 values. So let's see here. At 0.3, our instantaneous rate is going to be about 16.9. So let's see what that means. Well, remember that since it's changing, it's going positive, but it's going down. The spring is going down. So it's moving fast away from the ceiling. Here, negative 9.95, it's moving not as fast as it was earlier, but it's also moving toward the ceiling again. And here, at negative 0.55, when it's still moving toward the ceiling, but not very fast at all. It's almost stopped. So those are those values. So that's how we analyze this function. Okay, so we end with a couple of definitions. So, reviewing the derivative, we saw this last time, but it's good to see it. The instantaneous rate of change of f of x at x equals c is the limit of the average rate of change over the interval from x to c to x as x approaches c. Remember, it's that limiting value we saw that, when we get really, really close, because we technically can't find it at that point, c. But we get really, really close. It's a value that both sides get close to. We're going both ways. So that value is called the derivative. The meaning of the word derivative is shown here, and we'll learn a more precise mathematical definition when we're ready to calculate derivatives. But here's the meaning for this. It says the derivative of a function f of x at x equals c is the instantaneous rate of change of f of x with respect to x at x equals c. It's found numerically by taking the limit of the average rate over the interval from c to x as x approaches c, graphically by finding the slope of the tangent line to the graph at x equals c. Again, it's not something to 100% worry about right now. We're going to come back to that. But this is just kind of a preview so you can kind of see what the power that calculus has. So, with respect to x means that you're finding how fast y changes as x changes. Now, what we're trying to get to here is this definition of limit. We saw the average rate of change of the y values of the function got closer and closer to some fixed number as the change in the x values got closer and closer to 0. That fixed number is called the limit of the average rate of change in x as x approaches 0. As the change in x approaches 0, The following is a verbal definition of limit. It says L is the limit of f of x as x approaches c if and only if L is the one number you can keep f of x arbitrarily close to just by keeping x close enough to c, but not equal to c. So it means that if we get really close to c on either way, there's one number that f of x tends to go to, a value we would expect it to hit. It doesn't have to hit that value, but it also can. There's no reason why a limit why it can hit that value. It's just the value we expect. So that's kind of what we're getting at. We're looking at this kind of verbal definition. We're going to later see a better definition, but this is pretty good right now. So if you're following along and trying to do problems, I suggest doing problems 1 through 11, odds, number 12, and 13 through 17, odd. At the beginning, there's also the Q problems. They're quick review problems. They make a good review if you need it. I'm not going to say you need to do those, but if you are kind of, you need to review your pre-calculus and things like that, it couldn't hurt to try. All right, so that's all for this lesson. Hope you enjoyed the video, and as always, keep learning.